Okay, so today we are covering 9.2, Analyzing Rational Functions. Today we're going to demonstrate understanding of radical and rational functions with restrictions on the domain. So yesterday we learned transformations. Today we're going to learn what that graph looks like and to be able to tell the difference between a hole in the graph and an asymptote in the graph, and also how to find our x-intercepts. We should also be able to match a graph to the function with its equation. So again, we're just still dealing with graphs, but we're going to look at specifics of graph to find the x-intercept and the asymptotes and the holes that might be in a rational function. So where do you find the location of an x-intercept in the equation of a rational function? And where do you find the location of a vertical asymptote in the equation of a rational function? So when we're looking at a rational function, any factor that appears in the numerator corresponds to the location of an x-intercept. And any factor that appears in the denominator corresponds to the location of a vertical asymptote. So this is going to come in handy when we do some examples. We're going to end up factoring, and then that is going to let us know where our x-intercepts are and where our vertical asymptotes are. So let's take a look at example number 1. It says find any x-intercepts and vertical asymptotes in the following rational function. So remember, we just learned that our numerator contains our x-intercepts and our denominator contains our vertical asymptotes. So we can't see what those are right now, but we can factor. So what we're going to do is we're going to factor the top and bottom. So the top, if we look at it, we need to find sum and product. So we can find two factors that multiply together to give us -8 and add together to give us -2, which is x minus 4 and x plus 2. And we can do the same thing on the bottom, factor to find two things that multiply together to give us -6 and add together to give us -5. Which is -6 and plus 1. So we now have our factors, which is x minus 4 and x plus 2, and x minus 6 and x plus 1. They wanted to know the x-intercepts and the vertical asymptotes. So looking at the top, we can say that our x-intercepts are going to be found at x at 4 and 0 and -2 and 0. And if we look at our bottom, our vertical asymptotes are going to be found at x equals 6 and x equals -1. So just remember that our x-intercepts are found on the top and our vertical asymptotes are found on the bottom. So let's look at the function of a graph that has the same factor in both the numerator and denominator. If we end up factoring this, so we can factor the top and we get x plus 2 and x minus 1. And what happens is we actually end up having x plus 2 in both the numerator and the denominator. When the same factor is found in the denominator and the numerator, we have found this point to be indeterminate. What happens is there actually ends up being a hole at this point. So what happens is this actually crosses off our x plus 2 on the top and our x plus 2 on the bottom, and we're left with just x minus 1, which is just a line, and we have a hole at x equals -2. So we find x equals -2, and we have a hole consisting at that specific point. So when we have something that's the same in the numerator and the denominator, this point is called indeterminate, and it is not an asymptote. What happens is we actually have a hole at that point. We don't have a point, we have a point that does not exist right there. So when do we know that there is a hole in a rational function? We know that there is a hole in a rational function when there's the same factor found in both the numerator and the denominator. So an example would be just the one we just did. The last example that we're going to look at today are taking rational equations and matching them with their graph. So if we look at the very first rational expression that we're given. We're given k x equals x squared plus 2 over x squared minus x minus 2. We always want to factor the top and bottom to figure out what we're dealing with. So if we look at the very top, x squared plus 2, that can't be factored, it can't be simplified. But if we look at x squared minus x minus 2, that can be simplified to x minus 2 and x plus 1. If you remember to the very first example we did, these are where our vertical asymptotes are found. So we have a vertical asymptote at x equals 2 and x equals negative 1. And actually this should be x squared plus 2 on the top there. So we have vertical asymptotes at x equals 2 and x equals negative 1. And we know that this is going to be a parabola because it's an x squared. So we're dealing with a quadratic on the top. So if you look at the graph number 3, we end up having a vertical asymptote at x equals negative 1, x equals 2, and we have a parabola going on. So the graph kx equals graph number 3. Let's now take a look at the rational expression Lx. So if we look at Lx, again, the top doesn't factor, the bottom does. It's a difference of squares, so we get x minus 1 and x plus 1. You can see that we have something that crosses off here, the x minus 1 and the x minus 1. So we actually have a whole at x equals 1 and a vertical asymptote at x equals negative 1. Remember, this doesn't make a line. We actually end up getting 1 over x plus 1. So if you look up to graph number 1, we end up having a vertical asymptote at x equals negative 1 and a whole at x equals 1. So our answer for Lx is graph number 1. The last one is mx. If we look at mx, we can factor the top. We can factor it to x minus 3 and x minus 2. And on the bottom, we have a negative x plus 3. So all I did, if we look back at the original, was I just switched that so that our x came first. A lot of you are going to notice that we can actually take the negative out of the negative x plus 3. If we take the negative out, we get a negative times x minus 3, which ends up being the same as the factor on the top. So we actually get a whole at x equals 3. What happens is we're just left with x minus 2 over a minus 1, which actually ends up being a negative x minus 2, which is just a line with no asymptotes because we have nothing on the bottom anymore. But we still have our whole at x equals 3. So if we look at graph number 2, we have a whole at x equals 3, and we have a nice line. So the answer to mx is graph number 2.